Hello, my name is Nico Punt, and today I'm going to demonstrate to you the ATSIM++ visual pharmacokinetic pharmacodynamic modeling software. And this demonstration is based on a lecture I gave in April 2013 at the University of Groningen. But first, let me tell you a little bit about myself. I studied pharmacy at the University of Groningen from 81 to 86. Thereafter, I was involved in the research on calcium antagonists in ischemic heart disease. In 1990, I switched to software engineering at a company called Mediware, where I was involved in the development of MW Pharm, which is a TDM software program. In 96, I switched to IBM, where I did some completely different stuff. I was involved in embedded software development for digital video systems. In 1999, I founded my own company called Medimatics, and this company is mainly focused on software and PKPD model development. Let me give you an overview of my lecture. I will start with an introduction in which I will talk about the mission of ATSIM. Then I will explain the concept of object orientation, and I will do so using the famous Lego toy as a metaphor. Then I will tell something about the design of ATSIM, and important keywords here are models, objects, symbols, and desktop. Then I will continue with a short demonstration, and I'll finally come to the conclusions. But before I continue with my lecture, I want to make a critical remark by showing you a quote of the famous mathematician Samuel Karlin, dating from 1983. And he said that the purpose of models is not to fit the data, but to sharpen the questions. So what I think he means here is that you should not be completely fixated on getting the curve through the data points and maybe use all kinds of tricks in doing so, but instead you should focus on the model. So if your curve doesn't fit the data, you should ask yourself, okay, why isn't the model not completely correct, and what can I change in the model here? So what is ATSIM++? ATSIM++ is an object-oriented visual pharmacokinetic pharmacodynamic modeling tool for use in education and research. What is the mission of ATSIM++? Well, let me start by telling you what ATSIM++ is not. It is not a universal modeling tool that can be used in multiple application domains. There are some programs out there which actually try to do this, but this is usually associated with very complex software which is difficult to use. Instead, ATSIM++ focuses solely on PKPD modeling applications. And because of this clear choice, we managed to create a program that is very easy to use, but still very powerful. And one way of looking at ATSIM++ is as a kind of PKPD mind mapping tool. As already mentioned, ATSIM++ is an object-oriented modeling tool. So what is exactly object orientation? I will try to explain the concepts using the famous Lego construction toy. So what is important to know is that the objects in ATSIM++ are the building bricks of a model. And with the Lego toy, this is exactly the same. You have some basic bricks, basic brick objects, but you also have specialized objects like a window, a door, and roof elements. And of course, you need some platform to build on, and we call that the desktop. Now, when you put all these bricks together, you create a model. In this example, a very nice house. But what is important to understand is that with using the same basic building bricks, the same basic objects, you can build an entirely different house or houses. Just like Lego has many types of brick objects, ATSIM++ has many types of PKPD objects. And there are 7 basic categories. First we have compartments. And compartments can be regarded as containers holding a certain material, typically a drug. Then we have inputs. And inputs are those objects capable of adding material to a compartment. Its counterpart, of course, are outputs, objects capable of removing material from a compartment. Then we have transfer objects, which are capable of moving material from a source compartment to a target compartment. Next we have effect objects, which are able to calculate from a concentration or an amount or an other variable in a compartment the associated effect. There are also tool objects, which are used for many different kind of things, but one important application is here the calculation of, for instance, of the area under the curve. And finally we have a patient object. And we use the patient object for the allometric scaling of model parameters. And this is a very important feature because it allows us to use ATSIM++ models also for clinical applications. Please let me explain the architecture of ATSIM++ models. So at the top level we have a model which in fact represents a PKPD system. And the model is composed of a number of objects. And each object represents a PKPD process like absorption, distribution and elimination. In turn, each object is built out of a number of symbols. And all these symbols participate in PKPD equations. Like here, the equation describing the change in amount over time. As I already explained earlier, there are 7 basic ATSIM++ object categories. And each category has a number of different subtype implementations. For instance, if I look here at a compartment category, then we have a T-compartment object, which is essentially a central compartment, and we have a T-peripheral object, which is essentially a peripheral compartment. If I look at the transverse object, we have a one-way transport called T-transport, or a two-way transfer object called T-distribution. If you look at the input category, there are a number of input types like the basic input types, injection, infusion and absorption, but also the more advanced distribution functions like Weibull and gamma. We have on the output side also several subtypes. For instance, so we have the classical first order elimination, but we also have artificial outputs like the hemodialysis. And in the effect category we have the classical Emax model, but we also have several bacterial killing models. Now we have one special type of objects which we call interaction objects. And we see one in the transfer category. It's called T-competition, which is in fact used for modeling a pharmacokinetic interaction. And we have 2 examples of interaction objects in the effect category, being T-antagonism and T-synergism, and these can be used for modeling pharmacodynamic interactions. As I already explained earlier, symbols are the IDs that are used in mathematical equations. And we discriminate between 3 types of symbols. First we have constants, like fraction unbound. And constants are essentially invariant. They do not change, period. We have 2 subtypes of constants. One is called event constants, like dose, and the other is called option constants, like mode. And I will show you later on what exactly that means. The second type of symbols are parameters, for instance a rate constant. And parameters are time invariant, meaning that their values do not change during the time course of a simulation. However, their value may change between simulations, for instance, during a fitting process. And the third type of symbols are variables, for instance, concentration. And variables are time variant. They change during the time course of a simulation. And we have two subtypes of variables. First, we have interpolated variables, for instance, body weight. And these variables are not calculated using some formula, but they are simply interpolated based on available observations. And then we have differential variables, for instance, amount. And these variables need integration to obtain their values. I already told you earlier that the desktop is the platform on which you can build your models. And again, here demonstrated by our Lego example, we have this platform we call the desktop, and on the left side you have the basic categories of bricks you can use to build your model. And for ATSIM++, this is exactly the same. This is the ATSIM++ desktop on which you build models. And here on the left side you see the 7 basic object categories. And these are the bricks you can drag onto your desktop to create the models with. This slide gives you an overview of the demonstration I'm going to give now. And I will start with a pharmacokinetics example covering administration, distribution, metabolism, and excretion. Then I show you some pharmacodynamic models for modeling physiological effects and for antimicrobial effects. I will give you an example of non-linear kinetics using ethanol. Another example of artificial elimination, hemodialysis. And then I have 2 more advanced examples. One is about the enterohepatic circulation of mycophenolic acid, also known as MPA. And I will conclude with endocrine secretion of a glucose-insulin tolbutamide model. In this demonstration I'm going to show you how easy it is to create pharmacokinetic models using ATSIM++. I will start with adding a compartment to the desktop. I also add an input, and the default input is an injection. And if I connect it here to the central compartment, I have my first simple model. And one of the great things of ATSIM++ is that it's equipped with smart default values. So in the moment you created a model, you can directly simulate it. So I click here the simulate button, and we see this profile. So what we see is that we have repeated injections of 100 milligram every 8 hours. And we do this 10 times. And if I go back to my model tab and double click on this injection object, and I look at the object tab, object level tab, we see this dosage regimen, 100 milligram, 3 times a day, 10 times. Now, I want to change this input object from injections to absorption, first order absorption. I did this right now, and I can click again on the simulate button, and now we see this absorption profile. Of course, this is not really realistic because it's only accumulating. We have to add an output as well. So add an output. I connect the output. So this is a first order elimination, and I hit the run button again. And now you see the well-known classical oral absorption profile. Okay, what I want to do now is model distribution. So what I do is I add another compartment. And you see that the second compartment I add to the model is automatically a peripheral compartment. That's because your model can only have one central compartment. Now if I try to connect it like this, you see it's not possible. I have to connect it this way. And that is because the central compartment must be the source compartment. What you can also see is that this connection has 2 arrows. And that's because we are dealing with a bidirectional connection. So material can flow from the central compartment to the peripheral compartment and back again. This as opposed to the absorption input and elimination output, which are one-directional connections. Okay, so we added our peripheral compartment, so let's see what we get now if we simulate this. And here we see then the concentration in the peripheral compartment, C2. Okay, so let's focus on the elimination. Well, we could say that this elimination here only represents renal elimination. And now I want to add another pathway representing metabolic elimination. So I'll add another elimination object and connect it to the central compartment. And I could do a simulation, and what we see now is that we in fact doubled the elimination rate. But what I also want to do is discriminate between different metabolic pathways. And I can do that by adding a transfer object and change its type to metabolism. I will duplicate it for the second pathway. I will accumulate the metabolites in a compartment, so I duplicate this compartment, put it here, create another duplicate, and put it here. Now I can make the connections. Now, if I double click here on this transfer object and go to the parameters tab, I can state what the contribution is of this pathway to the total elimination. I could say, okay, 60% is eliminated through this pathway, metabolic pathway. And if I click here on this second pathway, I can say, okay, 30% is eliminated through this pathway. Okay, so let's do a simulation again. So here you saw again the concentration in the central and peripheral compartment. And what you see here are the accumulated amounts of metabolite. And what I of course could do is add an elimination output object to these metabolites as well. And then I have my normal profile. So central compartment, peripheral compartment, metabolite 1 and metabolite 2. Okay. So what I could do is I remove those again. And now I want to decorate my model. I want to make it more attractive visually. So what I can do is I can change the picture of the objects. And here, for instance, I could say, okay, this absorption was by giving a capsule. And this peripheral compartment actually represents the brain. And I could say this elimination, this is renal elimination. Of course, I can have a nice picture of the kidney. And for this metabolic elimination, I could use a picture of the liver. Now, and what I can also do is say, okay, these metabolic pathways, I could use a picture of the chemical structure of a drug. Just a simple example here. And another one. So in this way we can make our model visually more attractive, which is of course very handy in education. Okay, so what I will do is I start from scratch with a new model. Recreate it again. As you can see how fast this can go. So I simulate this again. And what I can do now is I can also show you these concentration profiles in the compartments they belong to. And I can do this by clicking on the mini charts button. And here you see directly a spatial view of the concentrations in the central compartment and the peripheral compartment. And if I now play a little bit here with the dosage schedule, and I could add another sequence, let's say 150 milligrams after 100 hours with an interval time of 12 hours and 5 dosages, and if I simulate this, you see it directly now in the compartment itself. And of course this combined view is still there, you can have a look at this as well. But they are in fact complementary. And of course I can change this also back to an absorption again, as we did earlier. Do simulation, and you see now the oral absorption profile again. So to conclude, this demonstrates how very easy it is to quickly create models and to simulate them and to experiment with them. In the next demo we will look at pharmacodynamics. So we will start with a simple one compartment model. And if I simulate this, you get this profile in the central compartment. And what I can do now is connect a simple Emacs model to the central compartment. I must say that I want to see the effect. I can do it right here. If I simulate again, you see the effect profile associated with the central compartment. I can play a little bit around with the parameter values. For instance, I can change EC50 to a lower value. Simulate again, and you see the effect levels go up. Okay, I'll now delete this effect object and we'll add another compartment, a peripheral compartment. Connect it, and now I will attach the same effect model, the Emacs model, to the peripheral compartment. Again, I want to see, observe the effects, and I simulate again. So now I see the effect here associated with the concentration in the peripheral compartment. So you see how easy it is to connect this effect objects to any of the compartments in your model. I also prepared a model demonstrating bacterial killing. And let me open that. So again, a simple one compartment system with an input and an output. And I connected this effect object called T-kill adaptive to the central compartment. And T-kill adaptive is an effect model modeling the adaptive killing of bacteria by an antibiotic. So let's simulate this, and let's look at the profile right here. So what you see here is the plasma concentration of the antibiotic, and this curve is the population of bacteria. So at high concentrations of antibiotic, the population diminishes because bacteria are killed. But if the concentration of the antibiotic gets lower and lower, bacteria start growing again. And this repeats itself for every dose. What you can also see is that there is a kind of adaptation. So during the time course of the simulation, bacteria start to grow more and more. In the next example, I will show you the consequences of nonlinear elimination. We will start with a simple one compartment model. And we'll not be using injections, but we'll be using an absorption. And if I simulate this, we get the oral absorption profile in the central compartment. So what I want to do now is I want to make a duplicate of this model. Simply select the model, click duplicate. So I have another model, two models on the desktop. And so now I can play a what-if scenario. I will change the dose to 200 milligrams, so I double it, while maintaining the same interval time. So let's have a look how it looks. So you see that the levels here are twice as high as the levels in the original model. And if I look here, you can see it even more clearly. I can make it even more easier by switching on the y-axis grid lines. You see here maximum levels amount to 150, and here maximum levels amount to 300 milligrams per liter. So this principle with linear kinetics is used as a rule of thumb in daily clinical practice. Simply double the dose and you will get double levels. Okay, now I also prepared a model with nonlinear kinetics. I will load it now. So again, two parallel models. And now we don't have a linear elimination, but we have a T-transformation object, which is implementing so-called Michaelis-Menten enzyme kinetics. And if I double-click this object and look at its parameters, you don't see the elimination rate constant, but you see those two Michaelis-Menten constants, being the key m and the Vmax, the maximum transformation rate. Okay, so and the values that are entered here are the values for ethanol. And also, if I look here at the compartments, this volume of distribution is the volume of distribution for ethanol. Now, let's look at the dosage regime here. So I have here a dosage regime of initially 50 grams, or let's say 50 cc of ethanol, a single dose. And thereafter we give 25 cc every 3 hours. So let's say a drink every 3 hours. And I do that for 9 times. So we give a total of 10 dosages. In the parallel model, if I click here, we do exactly the same, except the maintenance dose that we're going to repeat is twice as high, 50 cc. So I always ask my audience, what do you expect? The same kind of profile we saw earlier. Well, that will not be the case. If I simulate this, you already see here how much higher the levels are. And if I look here, you can see it's much higher, more than twice as high. And that's of course because of the nonlinear kinetics. And it's even worse because if I increase the number of dosages to, let's say, 99, so I give a total of 100 dosages, and I look here again, you can see that it will not reach steady state because the input rate is simply too high for the capacity of the, let's say, liver to transform the ethanol. So here you can see, well, that nonlinear dosing is complex, and how dangerous it can be when you drink too much. The next demo will be dealing with artificial elimination. Okay, we start again with a simple one compartment system. But this time we'll be using infusions. So I change this to infusion, and if I click here, you can see that there's an infusion duration set of 1 hour. And if I click simulate, then you get the profile looks like this. And what I can do is I increase the infusion rate, duration, let's say to 4 hours. And then the profile changes already a little bit. You can also set it to 7 hours. But what I will do is I will make it equal, the infusion duration, I will make it equal to the interval time. And I will be giving 20 dosages. And then you see it behaves like a one single continuous infusion. Okay, now I will add another output object. And it will be of type hemodialysis. and I connect it to the central compartment. Now, if I look at the object properties, I see here a opportunity to enter a hemodialysis schedule. And it looks like the dosing schedule you see with input objects. Well, you have the same with the output object. And so let's say that we want to have a flow of 1. And the first hemodialysis period starts after 40 hours. And it will have a duration of 10 hours. And we have another period also with a flow of 1 liter per hour at 80 hours and also a duration of 10 hours. Okay, and let's look how it looks like. So you can already see it here, but if I place a close look here, you see the effect of the hemodialysis period. So here's the continuous infusion. Here hemodialysis sets in. It's stopped again, so infusion is picking up again to steady state. Another hemodialysis period, and so on and so on. I can add a peripheral compartment just to see what the effect will be of a hemodialysis on peripheral levels. So if I simulate this again, you also see that the effect on the peripheral levels is less pronounced than the effect on the concentration in the central compartments. So now we will move on to some more advanced models. And the first example is a model demonstrating the enterohepatic circulation of mycophenolic acid. I already prepared a model for this demonstration, and I will open it now. So what you see here is a mycophenolic acid MPA disposition model, which starts with an absorption object, and here you see the central compartment object, from which the MPA is eliminated renally. MPA is also metabolized to MPAG, its glucuronide metabolite. MPA is also distributed to a peripheral compartment. In turn, MPAG is, for the most part, eliminated renally, but a small fraction is accumulated into the bile of the gallbladder. And as you know, with the functionality of the gallbladder, it will contract when fat food is taken. And so any drug that is also accumulated there will be excreted into the intestine again, which will allow it to be reabsorbed again. And so this phenomenon is called enterohepatic circulation or enterohepatic recirculation. Now, if I simulate this model, you get the following profile. So the blue line is MPA and the red line is MPAG, the metabolite. But you don't see any recirculation phenomena yet, because I have to activate it. And we use this special compartment object called T-portal to simulate this effect. And if I click here, you see that I can enter a schedule, just like a dosing schedule, but this time it's a schedule for controlling the transfer rate from the gallbladder to the intestine. And I can simply switch on this transport to simulate gallbladder contraction or emptying. So I can do it by entering a 1 here, and I can say, okay, I will do this after 4 hours. And it will keep working for 2 hours. And I can do it again, let's say after 10 hours, and it will keep working again for 2 hours. So these times then in fact represent the times of food intake. And this food intake will trigger the emptying of the gallbladder, letting the bile out again into the intestine so that it can be reabsorbed. Okay, let's see how this looks. So you can see that at 4 hours and after 10 hours there is a new peak of MPA. It is not because we added or given another dose of MPA, it's because the MPA that was accumulated into the bile is released by the food intake. So this is a very nice demonstration that you can also tackle more complex models using ATSIM++. So in the last demonstration of this presentation, I will be dealing with the most complex model so far, and it's about the glucose-insulin tolbutamide system. Now I already prepared a model for this demonstration. I open it. So what you see here is a generic compartment for modeling the kinetics of tolbutamide. Here is a specialized compartment implementing the so-called insulin minimal model. And this is another specialized compartment implementing the so-called glucose minimal model. So this is one of the approaches ATSIM takes, is that if you have very complex structures, you can isolate them into one model. And if I, for instance, double click here and look at the object level, I can click here on the code button, and then I see the source code of this insulin minimal model. I can make changes if I want to and recompile the library, or I can add new objects if I want to. Okay, now if I simulate this model as is, we get the following results. We just see the normal baseline values of insulin, which is about 5 milliunits per liter, and glucose, which is about 90 milligram per deciliter. What we're going to do now is we're going to give glucose to this patient. So I add here an input object and I'll change it to absorption. I connect it here, and then I double click. I change the units to grams, and I say, okay, I want to give 75 grams of glucose after 4 hours, and with an interval time of 8 hours, and I give 5 challenges of glucose. I also need to change the parameters here, because I know that the bioavailability of glucose should be around 0.5. Now, if I simulate this again, we get this typical healthy response. So here you have our glucose level, and here the glucose challenge starts. And almost immediately there is an insulin response. And the insulin response, insulin makes sure that the glucose is utilized again, so that the levels go down. And there's even an undershoot, as you can see. And this is repeated, this process, for every single glucose challenge. So this is for a healthy person. So let's try to simulate how a type 2 diabetes patient would behave in this context. So I double click here on the insulin compartment, and here you see the Emax model I used for modeling the tolbutamide effect. And what I did is I set the E0 parameter equal to the Emax parameter. So which means that there is already a large maximum response, so that's independent of the tolbutamide. So now let's add a more realistic value, and we put here, let's say, 0.5. So if I simulate this again, you can see that the glucose challenges have minimal effect in a type 2 diabetes patient. Not enough insulin is secreted, and you can see that the glucose reduction is slowed very much. The undershoot is also absent here. Okay, so we can follow two strategies here. We can either add insulin, or we're going to give this oral anti-diabetic drug, tolbutamide. So let's start with giving insulin. So I add another input object here. Again, it should be an absorption. And I must set the absorption parameters for insulin. And it's about 2. The absorption rate, the other parameters are okay. And now I click here. And I will give the, where do I have it, right here, the dose expressed in units, and I give 20 units of insulin starting at 12 hours, again interval time of 8 hours, and I give 3 dosages. And let's do the simulation. So again, here we don't give additional insulin and we have a poor response on the glucose challenge, and here we supply insulin manually by subcutaneous injection, and then we have a nice reduction in glucose levels again. Now I delete this addition of insulin so that we have our poor response again, and now we follow another strategy. We're going to add tolbutamide, also orally. I also have to change the absorption parameters of tolbutamide. I know that the bioavailability is about 0.993, and we have a standard absorption rate, and we're going to give a dosage of 1 gram starting at 8 hours, and we give a single dose. And let's see how this looks like. So here again, the initial poor insulin response on the glucose challenge. Here we give our oral anti-diabetic drug tolbutamide, and when the tolbutamide is on its maximum or close to its maximum, you see a very nice insulin response again on the glucose challenge. But you also see that when the levels of tolbutamide goes down, the insulin response goes down as well, so that you go back to the old situation. After this last demonstration, I come to my conclusions. First, ATSIM is very easy to use, as you have witnessed yourself now. Yet ATSIM is very powerful, as demonstrated by this last glucose-insulin model. ATSIM can be used for a broad range of PKPD modeling problems. And the PKPD object library can be extended by the end user. The user can do this using the built-in C# editor and compiler. And finally, ATSIM is very suitable for use in research and education. With the way ATSIM++ is designed, you will be able to really involve students in solving pharmacokinetic problems. It is this involvement that makes the difference. This is absolutely no new insight. It was Confucius who already said, "Tell me and I will forget, show me and I may remember, involve me and I will understand." Thank you for your attention.